All right, testing, 1, 2, 3. All right.
All right. Thanks everybody for coming out to Static Pi How and Why. My name's Adam Cammack, and that's Brent Cook right over there. I'm just kidding. Anyway, Adam, you want to go ahead and introduce yourself?
Yeah. So I'm Adam. I'm a fairly new developer at Rapid7 on Metasploit. Generally, I do more software engineering things than security things, but I like bringing software engineering into security, especially red team tools, because the more reliable we can make those, the better red teamers we can be, which makes everybody safer eventually, somehow. I also like Erlang and functional programming. That's just me, though. I've also been a musician for pretty much all my life, which is fun. I just got done playing a show in July, and I've got another musical that I'm playing right after I get back, so that's going to be a fun extension of Hangover Con.
All right. Hi, everybody. My name's Brent Cook. I put a few things, taking some inspiration from the other Rapid7 Adams talk yesterday. I talk about some things that I have done in the past, and one of them is I've been programming a lot of my life. Started with the Commodore 16 and did all my brother's CS homework and all that kind of stuff. I was just that kind of little brother. I've been a dad for 13 years. I got a kid who's almost in high school, so that's really exciting. And he's a good hacker as well. We've actually had like lockdown competitions where I lock down the home network and they have to figure out how to bust out and that kind of stuff. So it's kind of fun. I've been an OpenBSD developer for 3 years and a Metasploit developer for 2. So it's kind of an interesting little offensive defensive sort of paradigm there. You can follow me at Buster D. Cook on Twitter. I'm going to talk a little bit about executable file formats. You guys may be excited about that, or maybe not, I don't know. But we're going to talk a little bit about sort of the ABCs of different kinds of file formats you'll find in the wild for executables that run on computers. One of the oldest that's still kind of in use today is called A.out. A is for A.out. And it actually stood for assembler output. I actually used to think it meant like, A.out, B.out, C.out, whatever. But yeah, actually Ken Thompson used it in 1968. And the header for it is literally PDP-7 machine code so that you could just simply jump into it. So it really didn't have much of a structure. And that's the reason why a lot of like Linux distros like in the mid-90s like all switched away from this. But hey, this is what sort of formed the basis of the original Unix code. C is for .com. Well, I mean, not com, but you get it. Anyway, this originally started as a scripting extension for DEC mainframe operating systems, and then eventually CPM copied it, and then eventually MS-DOS copied it. And again, it's just not really that much of a format, but as much as just here's some code, jump into it, and have fun. It's a little bit limited. I think you can only get things so big, but hey, it's what worked in the early days. Quickly, things moved from COM to EXE. I don't know if you guys were much into MS-DOS or anything like that, or Windows 3.1, but you always had a sort of mixture of those. But EXE files can basically encapsulate a lot of different things, all the way from MS-DOS executables to Windows 10 and everything in between. It's actually used on a lot of different operating systems. BOS, for instance, used it under the covers in some areas. These days, usually you find portable executable COF binaries inside them, but you can find lots of other interesting things inside an EXE. M is for Mach-O. So Mach-O is what you signed in basically everything from Apple. They basically invented their own, basically their own ecosystem of linkers and libraries and core dump file formats and all that kind of stuff. One of the kind of neat things about it is it's easy to make a multi-architecture binary. And so this is, basically how Apple was able to go from PowerPC to x86 to back to ARM, and where they're going to go next. Maybe it's going to be, S390 or something like that. And E is also for ELF, so it kind of screw up our alphabetical kind of thing. But we're going to be talking a little bit about ELF today, and basically how to hack ELF for both defensive and offensive purposes. But it's basically the standard for pretty much every other Unix operating system other than OS X these days. So you find it in Solaris, HPUX, AIX, FreeBSD, Linux. Just pretty much everything uses pretty much the same file format to store their binaries. You want to go ahead and take that?
Yep. And one of the reasons we have ELF, or the big reason we have ELF, is because A.out was so inflexible. For example, the Linux implementation of A.out, every address was resolved at compile time. And so if you had more than like 3 libraries, you would have to figure out where to juggle all of that in your whatever 20 megabytes that you had on that Linux box. So we're going to walk through exactly how the people who came up with ELF designed it, and sort of a little bit of why they did, and then how we can abuse it for making binaries that just, work everywhere on routers and phones and stuff. So this is going to be a little bit of the original anatomy. Yeah, that's great. So there was a nice little flow diagram here of how the compilation process works. What you do is you've got source code, and then the compiler does the first pass over and produces what's called an object file. That object file is actually an ELF file. It's not an executable or anything else. It's just intermediate input for the linker, which will then read the ELF file and put out an actual ELF file that you can run on your system or link in a library or do whatever else you want to it. And so the original goals of ELF was that it was flexible. That was one of the big things that the original developers wanted it to be. So you've got two different views of looking at a file. You've got segments, which are what the operating system cares about, and then you've got sections, which are mostly just metadata or different ways of breaking up what actually gets loaded into memory. You can have arbitrary sections in data, like not all data has to be in a section, and you can make up your own random sections if you want, whatever. All the standard ELF tooling will still work with them. And each binary says exactly what it will do. There's no real convention other than here's the certain fields that are defined in the RFC, and if you have them, we'll do the special thing to them. And that allows it to be fairly universal. It works on most every architecture, or there's a version of ELF for most every architecture, which is pretty nifty. It's something that a lot of the formats you looked at earlier can't do. They're just specifically x86 or originally just PDP-7 because that's all people needed. But we've got operating systems now that run on lots of different chips. We need a file format that runs on lots of different chips. And this can do multiple Indianness modes, which is also fun. This had some diagrams which explained sort of the structural differences of the different types of binaries. So the simplest binary that you can build is what's called a static binary. It has typically two load sections, a code section and then a data section, and there's not a whole lot else in there besides code and data because it knows everything at runtime or everything at compile time. So everything is statically linked and placed into memory, and it loads from a fixed address every time, so exploiting those is super simple. Then there are dynamic libraries, which are a little bit more complicated. They have to have a couple of different program sections and a couple of different segments that static binaries don't need. It has to have an interpreter section. So every time you run a dynamic binary, which is most of the binaries on a modern operating system, it actually gets passed through another program before it actually starts running. Typically that's in /lib/ld. And it's pretty interesting that the operating system goes, oh, okay, I'll map this into memory, and then I'll jump into this completely different program that will eventually then bring up the binary. And that it'll do things like symbol resolution, so you'll need a symbol table and all the other sorts of things. And then shared libraries are almost exactly like dynamic executables, except their symbol table, which has the same name, is actually structured differently, which is always fun. And it doesn't have an interpreter section since it assumes anything that can find it knows what to do. So part of what enables ELF to do its magic is position-independent code, which is the compiler flag-f pick, and the runtime relinking. So while segments and sections are orthogonal and can point to all sorts of different things, you'll have both a dynamic section and a dynamic segment that point to the same code, and it's basically the section table, which doesn't get mapped into memory since it's not loadable and the operating system doesn't care about it. But it contains part of that inside of the dynamic section, which then allows the interpreter to go through and figure out what exactly it needs to do. It's got everything in there that you need, the type of dynamic object it is, or like where the symbols are, what address it wants to be loaded at, stuff like that. And Then there's a whole family of procedure linking tables and global offset tables. Some of them are in read-only memory, saying how it was compiled, and then some are in read-write memory, which is where it gets updated at compile time. Typically, whenever an executable is run, the interpreter will say, oh, here's all these symbols it wants. All right, they're all just going to point to me. And then when they're actually used, I'll go through and resolve them. And that's typically done for performance reasons, but it can lead to some interesting things during runtime, to where if you had resolved all the symbols up front, you would get different code than when you resolve them lazily, which is always fun.
All right. So I'm going to talk a little bit about ways that you can make ELT more secure than it is, and just basically some mitigation techniques and ways that you can screw up those mitigation techniques. Thankfully, I didn't include images in this section, so they actually translated over to the laptop. Basically, one of the sort of fundamental techniques that's used these days in most operating systems is the concept of address space randomization. What you basically do here is you want to make sure that if an attacker basically finds a flaw in the code, in order to exploit that flaw, you have to basically usually jump into some known offset within the code. By randomizing the different addresses within the code, you're basically able to make it less predictable and make it more difficult for an attacker to basically create a predictable attack. Oftentimes, an attacker has to do something like a heat spray, or they have to do some sort of information leak or some other way to figure out what the offsets of things are. This makes it just that much harder. Many different operating systems implement ASLR, which you actually, if you look it on Wikipedia, you can also look up ALSR, and it will automatically fix it for you. All the BSDs, except for FreeBSD, implement it. Linux, Windows, Solaris, kind of a surprising thing that FreeBSD doesn't have it yet. I think it's kind of a performance thing, but even as late as December of last year, they were still not sure if it was valuable for their operating system or not. So kind of an interesting thing. One catch, though, is that traditionally ASLR only works with dynamic executables. So what's a dynamic executable versus a static executable? Well, I'll show you an example here. So here's a simple program that basically prints where printf is. And so what it should show is basically the address of the offset where in libc printf is. I'm basically going to run some code on Ubuntu, the very latest version, 16.04, the latest stable version. And if you're just sort of like a naive guy, you go and like, oh, I'm just going to use GCC, build some code. What do you get? You basically get a completely predictable binary by default. Every time this binary runs, everything's at the same offset. Basically, if you had a vulnerability, you're basically either writing a CTF challenge or your code is going to be problematic in the field. We can solve this in a couple ways. We can build it as position independent. We can also build it as a portable position independent executable, or there's also a position independent code flag, depending on whether you're building a library or you're building a full-on binary. Something that position independent code solves is both the ability to relocate code from a security point of view, but also there are certain systems, and this actually dates way back to like the 60s and 70s, back when you would have multi-user systems that didn't have an MMU. There wasn't actually any memory protection. So when you wanted to actually load multiple pieces of code at the same time, you actually had to load them into physical separate offsets so that you didn't have conflicts between different pieces of code. So it's kind of funny that ALSR has actually been around for a lot longer than people were using it for a security point of view. So anyways, yeah, it's super easy. Like for instance, in GCC, you just add the position independent code flag, and suddenly you've got some lovely code that it's not exactly completely random. You can see there's at least on like say Linux, there's a lot of bits that are the same each time, but it is shuffled around a little bit. But then say you're a commercial developer, or you want to build some sort of code that doesn't depend on like all your system libraries, and instead keeps them along with you. So what you can basically do when you build an executable is put the static flag in. What that basically does is it pulls in all the dependent libraries and links them in as well right into the executable. So you don't rely on that external dependency. And you can see as soon as you do that, suddenly your code is static again, and it doesn't do any kind of randomization. So that's not good. And if you can just imagine, now that I switch slides, that there's a picture of like a boat capsizing. That's basically what should be happening here. So let's see. So we're going to talk a little bit about how you can sort of build binaries that are basically geared towards offensive use.
Yeah, there are There are a couple different kinds of binaries. The most common one that's talked about is shellcode, because that's what everyone has to write or rip out of Metasploit, which is fine. It's what we write it for. But there's a lot of constraints when building shellcode, where it has to be in assembly. And then you don't always know where you're going to be injected, especially with recent memory corruption exploits. You, like in JDuck Stagefright demo yesterday, you just don't know exactly where you're going to be. And so everything has to be relative to what you do know, which is where you are right now while you're running. So everything has to be relative to the program counter on ARM, or to the instruction pointer on x86, or to return of like mmap or something to wherever you map in or allocate memory. It's very time-consuming to write, not just because it's in assembly, but because you can't use a lot of nice, helpful tools. You have to structure your loads yourself, or how you manage the stack, or if the stack is even right. But the end result is something that's fairly robust, which is nice, but certainly couldn't write all of post-exploitation in assembly shellcode. That's just not maintainable. And so there's the next step of thing is you can build a static position-dependent executable, which means it doesn't need to touch the file system, which is good because you don't know what type of box you're compromising unless it's some sort of appliance that never gets updated, which if only that was all of them, but sadly not. And they're pretty easy to build. You just patch the static flag and it builds in everything, and then as long as you run it on sort of the same operating system, it works more often than not. But it does require specific memory address, which means if these people had some sort of memory sniffer agent in place, whenever that address got loaded, if you had to choose an uncommon one, then they would know that they were compromised, and it would be way too easy for them. Or maybe if you choose a random one and then recompile it each time before loading it, then you would have to just trust that you could clobber that memory, even if it held something important, like, you know, their heap that time, especially on if you're compromising a process that has address space randomization, then you don't know what you're going to be clobbering. Might have been useful, oh well. So if you could build a self-relocating static executable, then you wouldn't need to depend on the memory and on the memory layout, and you could use normal C code, which is difficult to write, but a lot easier than assembly code that you have to hand to golf. And so it would also simplify the shellcode you do have to write, because you don't have to worry about what you do if the memory is already taken, or if it's taken by multiple non-consecutive, or two different immaps are over the same block that you want to allocate. So if we could build one of those, that would be really nice. Turns out we can. OpenBSD 5.7 turned it on by default. So on OpenBSD, your binaries are independent, are position independent, and they don't load any other files once you start them. And Rich Felker of MuscleLibC has been working on this since 2012, mostly for embedded stuff, because on embedded systems you don't have an MMU, so you have to relocate every time you run the same, if you want to run more than one copy of the same code. And syncing dependencies between embedded boards is a giant pain in the butt.
So I'm going to talk a little bit about some prior things that we've done in Metasploit that both we and other people who've worked on Metasploit in the past have basically kind of laid the groundwork for what we're going to be presenting here today. I want to talk a little bit about reflected DLL injection and Windows Interpreter. I'm sure you guys know all about this. Who here has actually heard of reflective DLL injection? Anybody? All right, so I'm not going to bore you with a long thing, so I just put like a TLDR, because you can go to the GitHub page, you can read Stephen Fewer's paper, you can watch a lot of videos on that. But basically the idea here is that you have a little loader that basically bootstraps itself and is basically able to allocate all the memory that some portable executable code would go into. It does all the symbol resolution with kernel 32. It links everything together and then jumps into it. So it's kind of a neat little process. So it's basically kind of like a miniature C code loader that you inject into a running process. Very clever code, and we've used it to great success over the years, and a lot of projects have taken advantage of this as well. Something else that we've done we have something called Linux Posix interpreter. We've often called it Posix, but typically it's targeted just for Linux x86, 32-bit. Philip Sanderson did the sort of the foundational work there. What he basically did was he managed to port the Windows interpreter into Linux through a lot of kind of amazing hacks and changes to the code. But the basics of it is it basically embeds an entire copy of the Android Bionic libc and a custom linker that is able to basically embed all of the shared libraries that you need as zip archives into the running binary. It unzips these and then walks through all the symbols over and over again until they're all resolved. Basically does sort of a recursive resolver until everything's linked together and then jumps into it. So it's pretty amazing work. If you turn on the debug flag in Posix Interpreter, you can actually watch this stuff fly by on your console, and it's pretty fun to see. One of the sort of the limitations of this is while the shared libraries are position independent, the base executable is not. That actually causes some problems when you try to use Posix Interpreter or Linux Interpreter for doing actual exploitation, is because you can actually overlap with code segments that are actually already in use by your process. There's also, it's very hard to actually embed new libraries because you don't use a normal linker. You guys have to zip everything up and sort of do some special packing in order to get things built in. There's actually a little script that converts like the zip files then into like C code that then gets compiled, and so it's a little bit hard to extend, and requires a lot of sort of custom hacking. But that's basically how Linux Interpreter works. We're here to talk a little bit about sort of a new project that we've been working on for the past few months. And you want to go give it away? Yeah.
Yeah, so the new project we've been working on is called Metal. It's designed to be a stronger, more robust form of interpreter, which will allow us to use a lot of the same postcode we have, or what little of it we have for Linux, but it will allow us also to use Metasploit, which saves us a lot of time having to write that over again. So we took a slightly different approach to building Metal in that it was completely different. We use out-of-tree dependencies for most things that we can, so common libraries that you find in most C&C projects like curl and dnet and libev and embedTLS, which is a fun little TLS library from the ARM embedded group. But if we're going to use off-the-shelf, out-of-tree dependencies like this, we can't be building our payload with sort of the Byzantine Ubuntu 14.04 only half-working Docker image that we build current Linux interpreter with. And even once we do that, we're going to have to generate a process image that we can stick into a running executable if we want to use this for memory corruption attacks. So we just sort of have to do whatever the kernel does whenever it does its magic to load the executables, which is lots of magic. Luckily, some of it's documented in the sys5 release 4 ABI code, which tells you exactly how you should set up the stack and which, all that you need to do to make binaries happy and run themselves. And we had a nice little picture of that coming up, but it won't be there. So at this point, the shell code, all it has to do is it has to do the connect back or the bind, then it reads the process image off the wire into some memory somewhere, whatever. Then it has to push the magic values onto the stack and then jump to it, and then it should be done. Maybe, who knows? It works most of the time now. So I'll talk about the stack layout, and you'll just have to use your imagination. Sorry about that. So the stack looks a lot like it would look like from C. So you've got the first value is argc, which is the number of command line arguments you have. All right, that's fine. And then you've got your argv pointer array. Okay, so that's fine. And then you have some special null values. And after that comes all the magic that libc normally hides from you. After that, you've got what's called the oxv vector of pointers, which contains strings, pointers, other magic, to various process metadata that the kernel knows whenever it loads a process, and that libc needs to know some of, like whatever the RNG seed is going to be, or whether you're running as an elevated user, or what your load address was. And then that's followed by nulls, and then that's followed by another array of pointers for your environment, which is also needs to contain some magic sometimes, at least. Luckily, we were able to modify how we were building to not rely on environment variables, so it's just a couple of extra nulls stacked on the end. But getting the order right, and importantly, getting the Indianness right of a lot of those required lots of time staring at GDB memory dumps. And then we get to the part of how we can make generic code position independent and contain all the stuff it needs. So in order to do this, we have to abuse some linker flags. We have to pass some flags that look like they might be contradictory, like we pass both the shared library and the static linking flag, and we have to tell it to generate special relocations with -b symbolic. So shared, we need to generate a dynamic section that says we actually have symbols that we need to use, which your normal dynamic executable doesn't, so we have to pass that. And then we need to make sure that it doesn't, try to shell out to the system linker to reload it, because at that point you'd be touching disk, and it's probably under a different name, under different distros, or on Android it's in a completely different location that ignores the file system hierarchy, so need to get rid of that. And we need to pull in all the symbols, and once we can generate the special relocations that allow you to relocate your own process, we finally include a little bit of the magic that libc keeps for itself, so selfishly. And then we can build arbitrary C code to be injected into arbitrary memory locations, which is pretty fun. And on top of all of that, we need to make this work not just for x86, but for all of the architectures that run Linux, or at least the fun ones. So we have to cross-compile everything, which luckily we've got a lot of help from the embedded community, and since they need to cross-compile for everything. And so we were able to cobble together some scripts. Most of them are community now scripts that allow us to build statically linked toolchains for most any Linux processor. So MIPS Big Endian, and then there's a MIPS Little Endian processor. That's also fun. And then there's ARM Little Endian and ARM Big Endian now. And the different PowerPC and Power ISA architectures. So having a robust GCC support for that has been nice, instead of only being able to use the one GCC that came in Ubuntu 14.04 with a slightly broken linker. And we also had to use the Indianness conversion functions a lot, because you don't know what Indianness you were running at, which produced many subtle bugs and many glaring bugs that were very subtle to find. And then when you're debugging embedded code, it becomes very difficult to debug on the devices that you're running on, or it also becomes difficult to set up a full emulator. So QEMU doesn't have man pages for the user mode process, which is nice for running all of these obscure architectures. But QEMU user mode isn't documented in its man pages, which means it's slightly difficult to find handy ways like how you can get it to do strace output, which is incredibly useful. Did you die before the read or after the read? With normal QEMU, you don't know unless you spend an hour looking at the core dump. With strace, you can tell at least what you thought you were doing, which is fun. It also supports a GDB server, which is real nice for hooking it up to Radari 2 mostly, not GDB and GDB server mode. That's not fun. And we can also compile our binary for native targets, including we have gotten it running on OS X and pretty soon FreeBSD and native Linux, so that you compile it. You can skip all of the compiler magic just to get a normal binary for using it with normal debug tools, which is also incredibly helpful.
All right. So basically, what we've created here is a very compact, very fast, compact RAT more or less framework. It right now talks interpreter, but we're actually working on giving it some other ways to talk back. Other kinds of C2 channels. We basically abstracted everything out enough that we can add other kinds of integrations into the payload itself without necessarily being tied to interpreter's protocol. That's kind of one of our long-term plans. It uses less than 500K of RAM, and that's having loaded all the binaries and everything like that into memory. One of the reasons why it's a lot smaller than, say, like the existing Posix interpreter or other interpreters is because one is the embed TLS library is a lot smaller than OpenSSL, which is what we use on a lot of the other interpreters. Another reason is because we're able to statically link every function, we only take along with us the exact functions we use. So the linker is smart enough that it can strip out all of the other symbols out of the libraries that aren't in use, which definitely makes it a lot more compact. This is really important. We have some exploits that target routers like 16 megabytes of RAM. So being able to live comfortably without really affecting the performance or the stability of a small embedded device is, was one of our design goals. Like I said, it works on OS X and Linux. Also works on Android, and the stage fright exploit last week or yesterday was one of the things that was one of the first things to use it. One of the reasons why it was important to have a binary interpreter as opposed to the Java interpreter that we have today for Android is you weren't able to do things like exec due to SE Linux restrictions. So with this interpreter, we're able to sort of tune down and reduce the footprint as far as like what system calls it calls, what sort of things it does that normally get caught by mitigations. And as far as future work, things that we're working on right now, of course, is FreeBSD, OpenBSD, and Solaris support. We actually almost have it working on Windows as well. Which, because it's basically portable C code, you can build it with MinGW, and it'll produce an alternate binary that can speak interpreter protocol, but nothing in the world has seen yet. So it's kind of an interesting project there. We could even use reflective DLL injection. Something else that's kind of neat about this, the toolchain that we built, and we built it for OS X and Linux, is it can actually build any arbitrary binary. So you can build a Python that can be injected, or you can build a Ruby that can be injected, or pretty much anything you want, as long as you can bundle in all these shared libraries as part of the binary. Someone was joking about doing like a .NET integration, so we could actually run PowerShell on Linux within this interpreter. So that might be kind of fun to do in the future. Something else that we're looking at is makes it allowing it to be sort of a foothold for other payloads. Like I said, if you can build Python, then you can inject Python scripts without actually having to have Python installed on the Linux box. Or having to, sometimes people will apt-get install or they'll add things to the system. You can do this without doing any changes to the system, which is kind of a cool thing. I know typically IoT devices and stuff like that, no one's actually paying attention. You can throw things in var temp all you want, and there's really nothing to see. But we're sort of hoping that maybe people will start noticing, and we'll have some more interesting mitigations to be up against. But that's pretty much it. Today we actually have, like I said, cross tool chains for OS X and Linux. So basically you can target Linux from OS X in our build system. So you don't actually have to have a Linux box to build these payloads. We've got payloads working for ARM, Little Indian, Big Indian, MIPS, Big Indian, Little Indian. We need stagers. No one's written a PowerPC stager yet, so we could do PowerPC. I've run it inside of PowerPC running printers before. So we've gotten shells and printers and injected this payload via the firmware update process. Daryl Highland did some of the work and let me poke at some of his printers. So there's a whole lot of potential here for interesting things. So I hope everyone will be interested in it and check it out. We didn't put the actual URL where you can download it from, but basically go to rapid7.com/metal on GitHub, and that's where you can actually download it. That's it. So we have a demo, and we've got some interesting devices that we can make it run on. We have this Android monkey. Mark Stanislav did some research and found that basically this guy has complete root turned on. By default, it doesn't authenticate or anything. You just basically plug it in, it'll trust any device, and you can basically get a shell on this monkey, and we can run interpreter on him. We've also got, what else do we have? I've got a land turtle as well, and a Linksys router, which we can inject shellcode into as well. That's got 16 megabytes of RAM and runs interpreter as well. I thought maybe we could just go ahead and answer some questions while I'm busy seeing if my laptop will actually work this time.
We can do the Linksys too from this side.
Oh, you want to do the Linksys? Yeah. All right, why don't you go for Linksys then?
Yeah. Well, you can take questions while I set that up.
Oh, sure.
I wasn't ready.
Does anyone have any questions? No? Yes. Yeah, well, I mean, there's also Bear in the series, but yeah, this is just kind of an interesting thing. People are like, what the heck, he's got a camera in his nose. You can actually take pictures from it and send them back, which is kind of interesting. The company actually tried to avoid people getting into it, so they created like a fake USB device on the back, but there's a real one on the front. So yeah, he's charged only unless you sort of do a little reach around and suddenly. And that's when the party happens, right? It's actually kind of fun. When you boot him up, he actually has an adorable boot sequence here. Let's see if I can get him to turn on here in a second. Oh, a second. I got to turn him off first, then he'll boot up. Were there any other questions while I found the monkey? I mean, I didn't mean to say that. Linux powered monkey? I'm sure you just sigh. I'll bring it to Hackathon when the next come up, and we'll put it out. We usually have the masturbating monkey. Maybe that's before that. So let's see if we can get him to boot up here.
Okay, hold on while I boot up. Let's see. Fuzzy ears? Check. Round belly? Check. Little nose? Check. Cute little paws? Check.
I don't know what pies are.
Big round eyes? Check.
Dead eyes.
Gonna take a little more time, so a little bit longer.
Yeah, exactly.
I'm almost finished.
We've actually done some persistence. We built some persistence modules in-house for this monkey as well. I don't know how useful they are in the real world, but monkey persistence is really cool. You can. We've had him farting and all sorts of things. Oh, right. The boobop? Yeah. Are there any other questions about the details or what you want before?
So, like your cross-compiling tool chain is something you guys have put out as well?
Yeah. The tool chain is actually built into the make file, but we can release it separately. And the tool chain is actually built with the tool chain. So it itself is completely portable to any Linux system. So you don't have to actually run Arbor to run or anything like that. It's fully self-contained. It's a function library to run itself. So it built itself once. Yeah.
All right, any more questions?
Yeah.
I'm going to hack the router. Hack the Gibson. So this is a fun little worm that was discovered around 2.5 years ago now. It was called the moon worm. Basically, it's command injection in the login page to the router. It's really kind of a crappy bug. It's like, oh, what's your code? Oh, it's semicolon. Here, let me shell out for you. So it took over a bunch of Soho routers in 2014. And now it's going to demo for us. So it's pretty simple, just set L host and R host, and we'll set the new payload, and we run, we get the session, hey, and now we can see that we're there, and we do get UID. Turns out this is an embedded Linux system, and there's only one user, and it's root. So mission accomplished. And so we can do all sorts of nice and nasty things, like we can look at the routing table.
We can change the routing table.
And change the routing table. Or we can also shell out and access the non-volatile RAM and look at the administrator creds and harvest them that way. We can also, so many possibilities. We can, coming soon, we'll be able to pivot through the router. So if you compromise something on the other side, you can pivot through that box. Maybe it's ephemeral, maybe it's a phone or something that you know is going to go away. You can pivot back out to the local network interface on the router and establish a foothold there, and now you've got the network forever and ever and ever because no one reboots these things. Unless it gets slow, but since you're not using a whole lot of RAM, it won't get slow from you.
Any other questions? All right. Thanks for wrapping up.
So in that instance, I mean, you were kind of doing this semi-blind. Is it, did you have to know it was MIT's big Indian when you chose your payload, or?
This is actually MIT's little Indian. Well, it's built into the exploit, luckily. The people who dissected this router and built the modules, like, oh, this is a line of MIPS little Indian, and it automatically restricts you if we show options.
You're still
Oh, yeah.
Or background.
If we show options, we'll see that it requires a MIPSL payload. And normally the payload is to just exec to shell, is the default one, but the shell on that system is BusyBox. That was compiled with all the bells turned off. So it's a terribly painful experience. It has a half-functioning wget that you can then use to further stage stuff, but yeah, it's horrible. And there's not a whole lot of FS allocated, so it's actually a lot more reliable to inject the memory instead of trying to stage something to temp and then re-execing. All right, thanks to you all for coming out.